astrophysical phenomena taking place in the remotest corners of our galaxy are able to both horrify and amaze researchers of deep space. And today we will tell you about one of these things. The most powerful magnets in the universe with a staggeringly high level of radiation. Magnetars. Mankind has come across some extremely powerful radiation that reached us from deep space several times in the last 50 years. But as often is the case with space discoveries, the source was slow in being detected by astrophysicists. 1979. 3 US Vela satellites monitoring nuclear tests on the Earth detected an unusual gamma-ray flare. 1992. Astrophysicists assumed that there was a celestial object out there not known to science with a huge electromagnetic radiation coefficient. 1998. A gamma-ray flare in the constellation Aquila. A number of measuring devices registered an unaccountable anomaly with its source located tens of thousands of light-years away from us. 2004. All telescopes in the world were for a short time dazzled. Less than a second later, every cubic centimeter in the solar system experienced a wave of gamma-ray radiation. The most massive burst in the entire history of observations. And today we're closer than ever to finally putting our finger on the nature of this discovery. A magnetar is a neutron star with an exceptionally powerful magnetic field of about 10 to the power of 13 teslas, which in essence is trillions of times that of the electromagnetic radiation on the Earth. It is also one of the rarest and really most dangerous phenomena ever encountered by mankind. When a supermassive star is on the point of dying, a supernova occurs. Among the multiple scenarios of what may take place after that, only one may lead to the star becoming a magnetar after the supernova. Many of you would have heard about the Russian roulette at least once in your lives. According to the rules, only one cartridge is put in the revolver's cylinder. The chance of producing a shot after you have spun the cylinder is rather small. However, when it does happen, the consequences are truly mind-blowing. Be it as it may, scientists are still at odds over what exactly this scenario would look like. According to the first theory, it's the inner energy of the star and its rotational energy that influence the formation of a magnetar. If a neutron star is formed at the time of fast rotation, the inner energy of this star as well as its rotational energy, which is of great significance in the first several seconds, all create a powerful magnetic field. This process is known to science as a dynamo mechanism. But there is another theory as well. After the accretion process, the magnetar may be able to receive energy from another star. Scientists have discovered a magnetar which is on an escape trajectory from our galaxy. Most moving stars we know set off on their trajectories as a result of supernovae in binary systems. This means that the accretion process takes place between the two stars with a common mass center in a binary system. Matter from one star gradually flows to the other. In this case, this is the source of energy for a potential magnetar. Something similar happens with a basketball spinning around the edge of the basket. Sooner or later it is going to fall, but it's the spinning process that predefines the direction of the fall. Magnetars spin on their axes extremely fast, with a speed varying between tens and thousands of times per second. At the same time, their dimensions are record small. As a rule, the diameter of a magnetar reaches a measly 20 to 30 kilometers. Just to compare, the diameter of the Moon equals 3,474 kilometers. That is about 173 times that of the average magnetar. The mass, however, is a completely different matter. A magnetar with a diameter of 15 kilometers will be significantly heavier than our Sun, despite the dimensions. It is its staggeringly powerful density of the interior that is the reason for its high magnetic radiation. For instance, 1E1048.1-5937 is an anomalous X-ray pulsar located 9,000 light-years away in the constellation Carina. The star the Magnetar evolved from had the mass 30 to 40 times that of our Sun. The matter in these stars is dense to such a point that a fountain pen cap would weigh billions of tons, and a human would be torn to bits within a matter of seconds after landing on the star's surface. Several years ago, astronomers from NASA managed to register a phenomenon which came to be known as a starquake. Thanks to the Fermi Gamma-ray Space Telescope, scientists received data about intense X-ray bursts. Their source was Magnetar SGR J1550-5418. The magnetic field of this star is so powerful that from time to time its crust bursts with vast amounts of energy released through the crack. Such starquakes are the source of pulsed electric current. In theory, if a magnetar of this kind at its most active were to find itself within the boundaries of the solar system, we wouldn't as much as notice the threat, as the ozone layer of the Earth, together with all organic life forms, would be wiped off within a matter of a few hundredths of a second. Fortunately, however, the magnetar closest to us is a safe enough distance away. A magnetar is hard to approach not only due to the gravitational properties of its core and energy flares at the time of a starquake. When a magnetar is in its stable condition, its magnetic field is able to mess with electric devices hundreds of thousands of kilometers away, and within the radius of 1,000 kilometers, any object would be reduced to atoms. In order to systematize the difference in their radiation, scientists decided to divide magnetars into two varieties by using abbreviations. Rather than the full names, you will see these in any astronomical catalog. SGR, soft gamma repeater, and DXP, anomalous X-ray pulsar. In essence, SGR and DXP are different phases in the life of one and the same object. According to scientists, a magnetar exists as an SGR pulsar for the first 10,000 years. That is, it's a pulsar visible in regular light and repeatedly emitting bursts of soft gamma rays. As time goes by, it exhausts its properties and recedes into the invisible spectrum, when it can be seen to us only in the X-ray range, as an AXP. According to different sources, today among billions of neutron stars, the number of known potential magnetars ranges from 30 to 150. There are about 12 of them in the Milky Way, with the closest under the name 1E2259+586 being about 4 kiloparsecs or 13,000 light-years away from our Earth. The magnetar is a soft gamma repeater, and if a starquake were to take place on its surface, it would affect us only by some slight changes in the top layers of the ionosphere. Due to their small dimensions and remoteness relative to the Earth, magnetars cannot be observed through regular amateur telescopes. The method of infrared or X-ray scanning of the sky is usually employed to observe them. Nevertheless, thanks to their active magnetic field emission and radiation, these stars are much easier to detect with the use of various instruments. This is exactly what took place several years ago, in 2013. Astronomers claimed to have discovered a magnetar in close proximity to a supermassive black hole right in the middle of the Milky Way. The star was detected thanks to several orbital telescopes, including the Chandra X-ray Space Observatory. SGR 1745-2900 is only 0.3 light-years away from the edge of the black hole, and to date it remains the only neutron star to have been discovered in close proximity to an object of this scale. SGR 1745-2900 has been observed by scientists ever since its discovery. Several years ago, the level of its X-ray radiation was proclaimed to be significantly lower than that of the stars of this category. The news prompted numerous debates. Can these changes have been caused by the black hole in the star's environs? After 2 years of observing SGR 1745-2900, astrophysicists came to the conclusion that, all things considered, the distance of 0.3 light-years is insufficient for any interaction in the magnetic or gravitational field to take place between the black hole and the magnetar after all. The reason is likely to lurk elsewhere. A magnetar's lifespan is quite short, just about 1 million years, and it's quite natural for its magnetic field to gradually die down throughout the star's existence. Some scientists assume that these processes may be the reason for the change of the star's status. In this case, magnetars can switch their category, flare up more frequently or less often, deplete the stock of the matter, and thus go from the category of SGR to the category of AXP. In its autumn years, a former magnetar that managed to survive the dissipation of its magnetic field may even become quite a different kind of star, namely a thermally emitting neutron star. So far, just about 7 objects of the kind are known to science. For their number, this group has been dubbed the Magnificent Seven, and each of them may once have been one of the most dangerous objects of deep space. But in order to establish that, it will take us long years, further technological advancements, and dedicated people willing to devote their lives to searching for solutions to the most dangerous and incredible mysteries of the universe.